Next lecture is of Professor Elisabeth Larsson from University of Uppsala, Sweden. And so the topic is the approximation, multivariate approximation in imitations, in the problem of imitation of human respiratory. Okay, so please, Professor Larsson.
Thank you. I will share my screen. Okay, so I was very impressed by the previous speaker. My talk will not be as nicely kind of interactive. I will just show you pictures that are not moving or changing. So I'm sorry for that, but I hope that something can be of interest anyway. So I wanted to start with presenting my team. So we have actually a project which is interdisciplinary, and we have a medical doctor, Nicola Cacciani, and a medical imaging expert, Pierre Villard. And then there are my students, Igor, Ulrika, and Andreas, and a postdoc, Boštjan, who are working together with me. And I will present what we do from the application perspective, but the kind of approximation research that this leads us to. So the problem that has motivated this research, it's a condition that is called ventilator-induced diaphragmatic dysfunction, which of course many more people know about nowadays than before. But our medical colleague has been working on this for many years. So what happens when you place an intensive care patient in a mechanical ventilator? So instead of having the air is normally, in a way, it's sucked into your lungs when the diaphragm contracts, air is pulled in, but in the mechanical ventilator, the air is instead pushed in. And this damages the diaphragm, which is the muscle that would normally make you breathe, but it's not active when you're ventilated, and the muscle is stretched, and this damages the function of the muscle. And actually, it only takes 24 hours before you have severely impaired your function, your breathing function. And the goal of the project from a medical perspective is to understand this effect. How does it happen? What can we do to make it less severe? And how can we plan a good way to rehabilitate a patient so that the patient can be taken off the ventilator? So these are the medical questions, but of course, we are mathematicians, so we also want to look at other aspects, which we will come to. So the starting point, or some kind of starting point, is a medical image from a patient. In this medical image, we need to extract the diaphragm and perhaps also the ribs and the lungs and other structures that are important, but we're starting with the muscle part. It's really hard to find. So Pierre makes a segmentation mainly by hand, and this red part here is the diaphragm. And out of this segmentation, we get a point cloud with normals and data locations, but it's very noisy. We also have some additional data like pressure in the lungs and pressure in the abdomen, which we can use later for validation. But what do we want to do? We want to first reconstruct the geometry of the patient. So we want to build the patient in the computer, and then we want to simulate what happens in the muscle tissue when the patient is breathing normally and when the patient is put with the ventilator. Okay, so this is where our kind of more mathematical side comes in. So we want to do this with radial basis function approximation. And of course, there are many other methods you could use. Maybe you could use finite elements, which most people do. but we are interested in seeing how we can use these methods that are based on radial basis functions, because they are particularly good for smooth problems with smooth solutions. And we, at least we believe that this will be the case for the motion of the diaphragm. So when we use the radial basis functions, what we do is we take a linear combination of basis functions that are centered at different points that are scattered throughout the domain of interest. These are examples of Gaussian basis functions, and we see that we can add the shape parameter epsilon here to scale the basis functions according to the problem that we are solving, so that they are appropriate. And a nice thing here is that we can differentiate the basis functions analytically. So I look at it as a continuous approximation. It's not a discrete approximation. So another thing that is good with RBF approximation is that it's mesh-free. So the diaphragm it has a strange shape, and this helps us to treat this geometry. You can get a spectrally accurate approximation if your solution is smooth, of course. And maybe most importantly, it's quite easy to implement hard problems using these methods, because it's easy to express equations, conditions, and geometry. So the first step, it was to reconstruct the patient. So we want to make a surface representation of the diaphragm. A common method is to do an implicit surface using a level set where the zero level set is the surface. So in this picture here, you can see the object surface, and then you see the level set around that. It needs to be cheap. I mean, in the best case, we should be able to run this in a hospital, not on a supercomputer, but on a regular computer. So we use localized approximation because this is cheaper, of course. We make an infinitely smooth representation. This is, of course, not necessary. I mean, we could have a piecewise smooth patient, that would be okay. But we make it smooth because we want to have a high order PDE solving method later. And then we need the geometry to be smooth. And this is also reasonable from the physiological perspective that it would actually be smooth. And a typical problem in these type of methods is that you get a lot of spurious level set curves. So you get spurious level sets outside, you get them inside. And this is undesired because it makes it much harder to find the surface and to use the level set function. So, okay, then comes our experience and knowledge about the approximation theory. How can we use that? So in most methods, the basis functions are placed at the data locations. And the data locations are on the surface because that's the point cloud data that we have. But if we place all basis functions on the surface, this is not good for the approximation because it's not nicely distributed. So we decouple the basis functions from the data location. Then the diaphragm is very thin. It's like 5 millimeters, while at the same time it's as wide and deep as a human being. So it has a high aspect ratio. And then it helps us to use an anisotropic approximation so that we scale up the vertical direction or the thin direction. And we also put some extra conditions to help the approximation. And we use, there are different types of localized methods. Of course, we use a partitional unity method that we have adapted for the thin structure that we have. So in partitional unity approximation, your global approximation is built from a sum of local approximations on patches. So down here you see cylindrical patches that cover the diaphragm. So we have an RBF approximation in each cylinder, and then we add them together with partition unity weight functions to get a global solution.
Ah, per essere sicuro che puoi cambiare il giorno.
And all right, so we use one layer of patches, and this is of course because we have this special feature that we have a very thin geometry. Otherwise we could use several layers, or it wouldn't even be layers. And we adapt the patches to the geometry. So actually we use geometrically based adaptivity, or a kind of subdivision scheme perhaps. So all the patches that are too high, we can say, are subdivided, so they are flagged, and then we subdivide the patches that are the immediate neighbors of the thick patch. And then in the end, we get something that fits well to the geometry, also in the 3D case, not just the 2D. And then we finally add a desired overlap.
Ah, ok, che avevi sbagliato quelle cose lì.
And this is all done with standard methods. So we use a clustering algorithm to divide the point cloud into nice pieces, and then we fit the patches using principal component analysis, so it follows the surface. And yeah, this is it. So it's relatively simple, but of course, I mean, it didn't work immediately, but now it works nicely. Then we need to construct weight functions, and this is, it's not something difficult, but one has to think about the derivatives of the weight functions, because if they are too large, this will affect the properties of the surface. So basically, we want the weight functions to be 0 on the patch boundary and outside the patch. Or, well, this is not true. We want a generating function that is 0 on the patch boundary and positive inside, 0 outside. And with this function, we can use Shepard's method to normalize the generating functions, so that we get a function that is 1, where there is no overlap, and then it smoothly goes to 0 in an overlap region. So these two patches that you see here, these, when you add them in this overlap, they will be identically 1 together. But the trick here is to avoid having large gradient, and wherever two patches intersect at an outside boundary, you will have an infinite gradient, because the distance where you go from 0 to 1 becomes 0. So we need to make sure that the intersections are away from the data that we want to approximate. Then we come to, okay, so how do we make a problem that is robust and that gives us a good level set function? So we have a local RBF approximation with NC points, N center points. We use a multi-quadric RBF that is infinitely smooth. And we have an overdetermined local system. And the data that we use for the system, so let's see what we have in the picture, the crosses, the X's. These are the center points, and they are kind of evenly distributed in a patch here. Then we have conditions that the level set function should be 0 at all the data points. So these are the light blue ones. These are the data points. We want the level set to follow the given normals, but not exactly, because they are not good enough to require an exact following of these, but we want them to share a unit component in this direction. So it gives a little bit of flexibility for the level set function. And then, of course, we know that what will cause problems is the regions where we don't have data. So we actually add some artificial data when we are far away from the actual data point. So it's these colored dots. And then we use the distance to the data because the level set function is an approximate distance function. And yeah, there is a trick to that also because yeah, we don't know the distance exactly, and we also use the normal direction to compute it, but approximately like that. So then is the question, okay, how does it work? And what happens when we change different parameters? So the top one here, this is a 2D approximation because it's easier to illustrate. We see that it looks relatively nice. It's connected and it's relatively smooth. We have 21 basis function in each patch, and we have the height of the reference cylinder is 1 and the radius is 1. So it's slightly rectangular. If we increase the number of local points, as would be expected, we get an overfitting to the data. So we see that we get a lot more oscillations here because we have noisy data and we are not actually doing any regularization at this point. So we're just making a least squares fit. But then what happens if we change the height of the reference patch? So this is what I was talking about in the beginning, that we make an anisotropic approximation. And by making this h small, we are also making the thin dimension smaller in the approximation. And you see what happens down here is that the two surfaces are becoming too close to each other and the algorithm cannot recognize the difference. So it cuts off a little piece at the end, which is of course not what we want. So then we see that the anisotropicity is a good thing. And then finally, if we remove all the extra conditions that we put to stabilize the approximation, we get this, this very hairy approximation, which is not at all doing what we wanted to do. So it will be difficult to use because we will not know what is the true surface and what is junk around it. So these are the 2D and 3D reconstructions that we can make. They are infinitely differentiable because we are using weight functions that are infinitely differentiable, and the multi-quadrics are infinitely differentiable. So potentially, at least, we can have high order approximations in this geometry. Then we come to the PDE part. So we want to solve a PDE in this very thin geometry, and there are some challenges, of course, otherwise it wouldn't be so interesting to do. So we already talked about the geometry being quite complex, being non-parametric and being thin. So the first part was the representation. It's also difficult because if we have a uniform resolution in space, we will have problems of resolving the thin dimension without the cost becoming very high. And it could be hard to generate nodes to use by the method in this geometry. So these are geometric challenges. Then we have also PDE challenges. So typically for the diaphragm, most of the boundary conditions when we try to solve a problem are pressure conditions. So you have the pressure in the thorax, you have the pressure in the abdomen. And so these will be derivative conditions. And this leads to higher sensitivity or conditioning of the problem. And the problem becomes more sensitive to where we actually place the nodes. And then something that we have been looking into for quite a while actually is to use oversampled methods, because the oversampling, it helps the stability of the method, it decreases the sensitivity. And the first oversample method that we did was a partitional unity method with Sherbakov and Haryudonov in 2017, but I will not talk about that now because I wanted to talk about the stencil, oversampled stencil method instead. So this is recent with Tominets and Haryudonov. And we have also used So the problem with being thin, it's helped by using an unfitted method. So with unfitted, I mean, like in this picture, the blue points are the nodes, and these are now outside on the domain as well as inside. And in this way, we get kind of an artificial thickness that we didn't have before. Unfitted, yes. And the unfitted approach also helps with stabilizing the approximations of the derivative boundary conditions. And this is because you don't have to have skewed stencils at the boundary. But we haven't really talked about stencils yet. So we go to the stencil slide. So when we use stencils and RBF methods together, so typically we have scatter nodes. So if we have this red point XC, typically we pick the nearest neighbors of these points to form a stencil. We are using right here, we are using a combination of the polyharmonic spline, R cube, and the monomial basis. And we form a little interpolant on this stencil, and we use this to compute derivatives. And yeah, so what is the oversampled thing? So normally when we use a stencil approximation, we only use the stencil in the center point. But if we use one stencil in more points, in our case, we use these blue points. And what is describing these blue points is that they are the points that are closest to the stencil center. So we get a little Voronoi region around the stencil center. So we use this stencil, we use it in 1, 2, 3, 4, 5, 6, 7 points. And we get a rectangular global system because we have more blue points in the rows than we have red points in the columns. And to compute the derivative here in the same way as I showed before, we differentiate each basis function analytically. But something that is special with the RBF-FT approximation, not special in a good way, but special perhaps in a bad way, is that this hopping with stencils, it creates a small discontinuity. So in this Voronoi region, we use this stencil. In the next one, we use another stencil. So we will not have continuity between different regions. But it can be shown that this jump is small and that it goes to 0 when we refine. And this is, so maybe I should start with this part. So this is a little bit heavier, and we will see how it goes with that. So how can we analyze this discontinuous approximation is the question. How can we understand how it converges? If the error will be small, how good it is. So it is often a good way to consider a continuous problem and a continuous approximation and try to understand how that works. So this is what we will do. And we will do this for a Poisson problem with a mixed boundary condition, Dirichlet and Neumann conditions. And we introduce the normal L2 norm, continuous L2 norm on the domain. And we also introduce a space, which in this case is homogeneous for the Dirichlet boundary, because this is helping our analysis. It's not a restriction in any way, because we can just reformulate the problem so that it fits in this way. So if we write down a least squares problem for the Poisson problem, we want to minimize the residual of the interior Poisson equation, the residual of the Neumann boundary condition, and the residual of the Dirichlet boundary condition, each of these in its own domain. And we can write that using the techniques from finite elements, really. We can rewrite that as a bilinear form of U and V equals a linear functional of f and v for all functions in the space V or V0. And the bilinear form, this will then be the inner product of the Laplacians, the inner product of the normal derivatives, and the inner product of the functions themselves on the Dirichlet boundary. But the point of all this writing things in a different way is that now we can show that this bilinear form for the continuous problem for two continuously integrable derivatives, we can show that this is coercive. So there is a lower bound for this bilinear form in terms of the norm of this function in this space. And this is, this is typically finite element approach. But we are not directly done because our function space, it's not the subspace of W22 because it's discontinuous. So we will take a step. We will start with a discrete norm, which is what we actually have, and we will go to semi-discrete space, and then we will go to the continuous space. So this red function, VH, this is a function in the discontinuous trial space of RBF-FT approximations. And our discrete norm, this is given by a sum over all of these blue points that I showed you before. So yi, these are the blue points, and this omega over m, this is like an integration weight. So this is a discrete quadrature that is approximating a continuous quadrature. And we are going to take it in two steps because our functions are piecewise continuous or piecewise smooth, partly smooth at least. So we have a semi-discrete norm where we take the L2 norm over each Voronoi region, and then we sum this together. And the point now is that by having this view on our approximation, we can start by relating the discrete and the semi-discrete problem by making an integration estimate. In 1D, it's easy to see that each of these, it's a Riemann sum, but with the point moving around a little bit. And it's easy to bound. It's much harder to do it in 2D and 3D and so on, but you can bound the integration error and you get a relation between the discrete function and the discrete norm to the discrete function or discontinuous function in the semi-discrete norm. And you can do the same with the bilinear form. And this integration error, this will become smaller when we increase the number of blue points, the oversampling points. The more we have, the more continuous the problem becomes. And then we need to go from the semi-discrete to the continuous. And this is another type of difference. So we have a piecewise continuous function, and we smooth this function. So for now, S is a smoothing operator that creates a smooth function, which is in the Sobolev space that we need. And well, we don't do this smoothing for real when we implement the method, but the smoothing is done. We do it theoretically to prove the point. So, but we use partition of unity as an argument. So we take a function which is discontinuous in the sense that, we have the red one, we have the blue one, and they don't exactly meet each other smoothly. And then we add this partition of unity blending, which is a little wiggle. And then to estimate the errors between the discontinuous trial space and the smoothed function, we need to estimate the size of this wiggle. And this is a little bit more tricky to do, but it can be done. And we can, we don't exactly compute a number, but we can show what is the dependence on the step size or not, and so on. And this smoothing in a practical problem, it will become smaller if we have more smooth data so that the functions fit better together. But it doesn't change with the oversampling. This is independent of the oversampling. And now we can put these pieces together. So now we will move from the starting point. This is the discontinuous trial function. It's the discrete norm where we sum over all the blue points. And then we start with the integration error to get the semi-discrete norm. Then we have the smoothing error so that we get the continuous norm. And then we have the coercivity, because we can use that for the function v. We couldn't use it for vh because it's not in the space, but we can use it for v. So we come to the bilinear form, and then we go backwards. We do a smoothing estimate to get to the discontinuous trial function, and we do an integration error estimate to get to the discrete bilinear form. And then this actually, what we have here is coercivity for the discontinuous trial space and the discrete norm, which is nice. And of course, now it should be noted that, like I said, this tau, it has to be smaller than 1. Otherwise, we don't have coercivity. But what we can see then is we have coercivity if the oversampling is large enough, because then tau will be small enough and everything will be nice. And of course, then to do convergence, we also need consistency. And if we have a stencil where we have used a polynomial basis of degree k, and then this means that we need a certain stencil size so that we support this polynomial and a little bit more, and that the points should be well distributed with respect to the polynomial basis so that it's not degenerate, then we can use basically Taylor expansion with some extra stuff added to see that we have a consistency error that is the polynomial degree plus 1 minus alpha, which is the order of the operator that is applied. And h is, as usual, a measure of the node distance. So then we get the convergence estimate. We can, with a few steps, we can show that the error in the discrete norm is bounded by this discrete stability constant, and then it goes with a rate that depends on the polynomial degree, as long as the function is sufficiently smooth to allow that order of convergence. And this is actually very nice. It's just what we need. And we have also done experiments to show that this is what we truly get. So the bounds are good in the sense that they reflect the actual results. And I'm not going to show you a million experiments. I will just show you a little bit. So we have here a runtime comparison, because for an application, the bottom line should, in general, be what time does it take to get your required error tolerance. And the black curve here, this is collocation. What does that mean? It means that it's not oversampled. So oversampling equals 1 or m equals n. And this curve it has a little bit of going up and down. It's not as robust. It still works, but it doesn't work as well. And you can see that in each case of oversampling, we have oversampling with a factor of 3, 4, and 5. They are all faster than no oversampling, which is very nice. So it means that since we do a bit more work, but the error is reduced enough so that it doesn't cost more than what we get. And actually, it turns out that the reduction due to increasing the oversampling is going with the same rate as the increase of the cost. So that in this case, it doesn't matter what oversampling we take. They are all kind of equal in terms of time to get a certain tolerance. And this was not completely expected, but interesting. So how far have we come with the real problems? Well, we still have quite a long way to go. But this is also interesting that there are many things to try and to learn and to research. So we have solved linear elasticity problems. We have solved them in a cross section. We have actually solved them in 3D also, but we don't have any finished results. And what you see here is the von Mises stress of the diaphragm, and we actually have fake boundary conditions. So we have taken the boundary conditions from the medical images, but they are constructed to mimic what actually happens. So what we should see is that the diaphragm moves down vertically in the upper part, which is stiff, and that we get a contraction here where the muscle is, the contracting part is on the sides. So with the fake problem, we are able to mimic the results that we, from a medical perspective, think that we should get. So it is something. And we are also doing this with high order convergence, which is from a numerical perspective, very nice. And this is done with the oversampled RBF-FT method. It's also unfitted. And we have also looked at smoothed boundary conditions, because this is, of course, something really hard. When you have a real problem, you want your solution to be smooth, but if you impose boundary conditions that are not compatible, your solution will not be smooth. And in this problem, what we have done is we have made a smooth transition between the traction and the Dirichlet boundary conditions in order to preserve the smoothness of the solution. But this is, of course, another modeling parameter that should somehow reflect reality. This is another example. Here we have used the unfitted RBF-FT method on the 3D diaphragm, but the problem here is just a Poisson problem right now, using mixed boundary conditions. So the unfitted nodes, you see the blue ones are outside, the red ones are inside. And the error is larger on the inside because this is where the Neumann boundary condition is applied, and this is a typical behavior. But also in these experiments, although, I mean, they are a little bit too simple, but we got very nice high order convergence rates, so that is good. And my final slide. So what have we done so far? So we're trying to simulate the breathing of a human being. We are certainly not there, but we have been able to reconstruct the diaphragm in a way that we know is robust. So there won't be holes, there won't be problems, because we know that we have control over the level set function. But we need, of course, a proper tissue model for the diaphragm, and nobody actually has the answer to what is the appropriate tissue model. We have to use data, we have to use experimental results and so on to try to figure out this using our validation information. It has to have active muscle contraction, so this has to be part of the model, which makes it extra nonlinear, because it's probably nonlinear in any case due to the tissue model. And we need to have proper boundary conditions that take into account the actual pressure that you would expect to have in the abdomen and in the thorax, and the attachments to the ribs and so on. So there are many practical things. So this is the typical thing when trying to solve a real problem, that there are many practical issues. And then, of course, there are more theoretical issues as well. But in any case, it is very nice. And I also put in a dragon here that I made today. So we were trying to see, can we use the method to reconstruct more strange geometries? And we can, but this is, it's not really following the requirements we have, and it was really hard to make, but I thought it was fun anyway. And thank you very much for listening, and let me know if you have any questions.
Thank you, Professor Larsson. Please, questions. Maybe I start with the questions. I have two. First of all, could you come back to the slide number 21 with this smoothified boundary condition? Yeah, smooth boundary conditions. So how do you actually smoothify it? So what do you use to do that? Because, yeah, because you should not, the smoothification should not influence very much the solution. Yeah, and so
yeah, this is the problem, of course.
Mm-hmm.
Now I don't remember what exact function, but it was a typical, like a logistic function, but not too steep, something like that. And of course, it does affect the solution. If you make it too narrow, it affects your solution because it's hard to approximate. You have to resolve this narrow transition. If you make it too wide, you change the boundary conditions because then you get a mix of fixing and following the pressure, which is unphysical. So yeah, this is a hard question. What is correct? But of course, when we look at the diaphragm that is attached to a rib, this will not be attached at one point. It will be attached, and it will be attached elastically. And yeah, how do we model this in a reasonable way? I don't know. But I mean, yeah, we need to, in order to have a problem that is fixed, which we will need, we have to decide what is a reasonable smoothing radius for an attachment to a rib. Is it the size of the rib, perhaps?
But what are the tools of your smoothification? I mean, do you approximate it with some kind of polynomials? I don't know, or do you convolve? Do you consider convolutions with a smooth function? So you have a problem with non-smooth boundary condition, yeah? And what kind of method do you use to smoothify it?
Yeah, so say that here you have the traction condition coming in.
And
yeah. Here you have the Dirichlet condition. Here they meet. But instead of having a constant coefficient on each, we let them overlap. And then we have like a partitional unity function, say, that goes down to 0 for this one, and that goes down to 0 for this one. So they overlap. So we will have a robbing condition in the middle.
Okay, yeah. Yes, thank you. So more questions.
Is it important what radial function to use for applications?
That's a good question. So we use the multi-quadric for the geometry reconstruction. And the reason is that, well, one thing, we wanted a smooth basis function, and there are a few infinitely smooth ones to choose from. But the multi-quadric is well behaved both when you have a scaling so that the function is narrow and when you have a scaling so that the function is wide, or well, in some sense. So we chose it because we know that it's relatively robust. For the stencils, I mean, people have been using different things, but it turns out that Bayona, Fornberg, and Flyer, they came up with this idea, I think at least, by using a polyharmonic spline together with a high order polynomial. And it has been shown theoretically that this combination has very nice properties, both at boundaries and in terms of approximation power. So I think nowadays people think that this is a very good option for Stencil. So it's not, other basis functions are less used for Stencil approximations.
Thanks.
Please, questions? Maybe I ask the second question I had in mind. Unfortunately, I don't remember the number of the slide. It was somewhere in the beginning when you approximate some very narrow domain by kind of subdivision. with
Here.
yeah, yeah, it's here. So is this one-dimensional, two-dimensional picture? I mean, is this a curve or this is a surface?
So I mean, the example here, this is 2D, so it's made in 2D to illustrate the idea. But we do the same thing for the 3D problem. But then, of course, the subdivision, we still use the thickness as measure, but the subdivision is then done in 2 dimensions.
So this, you also do this for surfaces, yeah?
Yes.
And then much later, you showed another approach with the oversampling by a function of partition of unity property, yeah? And so my question is, so you use basically this at least 2 methods to approximate the narrow domains, yeah, by subdivision and by oversampling.
Yes. So yeah, there are different components.
Yeah. Why do you use one in the one problem and another one in another? So what is the difference?
We use subdivision. We use in both cases, and actually we also use oversampling in both cases. So the problem here that you see for the geometry, it's also oversampled because we have more data than we have basis functions.
But in oversampling, as far as I understand, maybe I'm mistaken, but in oversampling, you shouldn't have these overlapping problems, or not? Because
you can have this.
Sorry?
This is not the problem. I mean, you can oversample anything. So it's just that we write the approximation in different ways. The global function is given in different ways, but you can, where do I have it? I mean, here the function is a sum, but this doesn't matter. You can still oversample by collocating your approximation at many different points.
Yes. But when in the beginning, when you showed us the subdivision, then you had the problems with overlapping of 2 functions, yes, and you showed how to treat it. Yeah, so if the neighboring functions have overlapping supports, yeah, then you showed how to.
You mean the weight function, I think.
Yes.
Yes.
Yeah.
So these are kind of different parts. So the weight function is needed to build the global approximation, but it doesn't contribute to the approximation in the sense that the other part does. So the RBF approximation is what we need to work with, and the weight functions are just glue in a sense.
Okay, thank you. So if there are more questions, if not, let's thank the speaker. So this is my applause. Thanks very much, Elizabeth.